All right, now we're going to check out part C. We already looked at part C a little bit earlier to compare what it meant to find the average value of a function to the average rate of a function. So the average value of the function means I'm going to think about, with this piecewise function, let me bring it back over here. With this piecewise function, we're going to need definite integrals, okay? If we have a piecewise function where the domain is separated, then that means I need a separate definite integral for each piece. But I'm still thinking about that it's over one large interval. So let me show you what I mean. 1 over 4 minus negative 3, the length of this entire interval. And then that's multiplied by the two separate definite integrals added together. The first piece starts at negative 3 and goes to 0. And that piece is the square root of 9 minus x squared dx. The other piece is from 0 to 4 of negative x plus 3 cosine pi over 2x dx. All right, so first of all, we got points just for getting this done. Setting up the definite integral correctly and then understanding that it was average value of a function. I saw a lot of funky things here, so I could see a lot of misunderstanding. So I want you to see here one large interval over this entire area under this curve, the two definite integrals added together. So let me focus first on this guy. Try to color code them a little bit. If I quickly sketch what that graph looks like, and again, you could check out Desmos if you wanted to. This is the definition of a circle here, any square root function like this. So from negative 3 to 0, this would be usually a semicircle that goes from negative 3 to 3, but I'm just looking at a quarter circle here based on the limits of the definite integral. So for this first piece, I'm going to think about the area under that curve. The value of the definite integral is pi times the radius of 3 squared, but not for the whole circle, just this quarter of a piece. So I'm going to divide by 4. Okay? And then on the other side, I am going to have to use antiderivatives and u substitution here because I've got a composition of a function. So a lot of you guys did that correctly. You remembered your antiderivatives. Here we add 1 to the exponent, divide by the new exponent. For antiderivatives, we still have a constant multiple rule of 3. Okay? The antiderivative here of, I lost where my work is, sorry guys. Antiderivative of a positive cosine is positive sine. And you could also remember plugging in u substitution here, but we also studied in chapter 7 quite a bit, just memorizing that if we've got a composition of functions that's easy, that's linear inside a trig function like this, that we can just divide by that linear piece, that coefficient. So divide by pi over 2. So I'm going to even adapt this further. I'm going to multiply by the reciprocal here, multiply by 2 over pi. Hopefully that looks familiar, because I know we did problems where we had to multiply by this sort of funky looking radian reciprocal and other trig functions when we were in class together. And now we plug in 4 and 0. When I plug in 4 here, I'm going to think about plugging in 4 and 0 first to this big trig function. When I plug in 4 divided by 2 is 2 pi. Sine of 2 pi is 0. So this whole thing wipes out, right? Here's my unit circle again. I'm back here. Sine is the y coordinate here. So this is all 0 at 4. And then when I think about plugging in x equals 0, pi over 2 times 0 is 0. Sine of 0 is 0. This whole thing wipes out. So no matter what I'm looking at here, this all goes away. So I'm really just plugging in 4 here. And then I could think about plugging in 0, but that's going to go away as well. So I'm just negative 4 squared over 2 minus 0. So 4 squared is 16. Negative 16 divided by 2 gives me negative 8. Okay? And now we need to put all of this together. So we have 4 minus negative 3. So we've got 1/7. We've got the area of the quarter circle, 9 pi over 4, which you could use as a decimal if you want, and then minus 8. A lot of you guys use the graphing calculator here and Math 9, where you could plug in the value and get the answer to your definite integral. In this case, I'm not sure how that would be scored. This was originally a no calculator problem, so a lot of the scoring rubric asks you to show definite integrals, to show you the antiderivative. So I want you guys to practice that, because this FRQ that you're going to be taking on Tuesday, since there's no more multiple choice, you may have to make sure you show that you understand these antiderivative rules that you've studied, because there won't be any multiple choice questions on this year's test to show those skill-based types of problems. So you could check your work on Math 9 if you've got time, but otherwise, this intention of this problem originally was to do it by hand like this.